Muito bem, boa tarde. Então, bem-vindos ao segundo minicurso. Bom, cronologicamente é o segundo, mas é o terceiro minicurso 03 aqui do nosso programa temático. E essa é a primeira aula dada pelo professor Ascher, da British Columbia. Então, prazer tê-lo aqui novamente. Vou passar para vocês agora uma lista de presença. Por favor, não saiam sem assinar. Please, go ahead.
Obrigado. Eu falo pouco português. Então, eu vou falar inglês, claro, mas porque tem argentinos aqui. Mas se você tem perguntas, pode perguntar. E se você quer falar português, pode perguntar em português mais lentamente, por favor. And agora, I will now switch to English and stay with English. The truth is I can only teach in English, even though I know another language. My lingua de mai is not English, but I still can teach only in English. So, I'm going to give 4 lectures, and the topics will vary quite a bit from one to another. But there are some connections in my mind from one to the other, but they are weak connections. It's like a piecewise smooth function. You know, from one lecture to the other is barely continuous, yeah? But within each lecture, hopefully, it is a bit more smooth. So the first one today will be about calibration and simulation of deformable objects. And so you have an object like this, which is deformable. Or you have these seats that you're sitting on. You apply a weight when you sit, and the surface changes by this. And that is different from this rigid body, right? That when it moves, it has only 6 degrees of freedom. A deformable body will be some sort of a surface moving, a body moving, but the surface changes, many more degrees of freedom, and much more complicated problems. And so the question is how to calibrate, which means solve inverse problems to find the properties of the material, for example. And others, we'll see. And the simulation, how do you simulate that to solve the forward problem in the inverse problem context? So one of the things that I show you has to do with manipulation of data. And that leads us, or at least me, to the second topic, which is data manipulation and completion. And as I said, the connection is continuous, but not more than continuous. And we will talk about various case studies of data completion. One of them, in fact, is joint work with Georges Zubelli and 2 other people who are no longer here, I think. Xu Yang. Hi, Xu. Como vai? and Vinicius Albani, who stayed, I think, tá bom, muito bom. And another one would have to do with PDEs with many right-hand sides. And this would lead us to the third talk, which talks about the trace of a large implicit matrix, which sounds totally independent of the other one. So you have a very large matrix, and you want the trace, but you cannot look at the diagonal elements. So you cannot just sum up the diagonal elements because you don't have the matrix. All you have is implicitly the matrix times vector, but not the matrix itself. And I will explain why it is important and how to do it. This also has to do with events that took place in Brazil. In particular, there was a workshop not in Areal do Cabo, in Cabo Frio, a few years ago. And my student, Fred Rusta, was there. And so was Pierre de Gon, who is a famous French mathematician. And I presented our work there, and Pierre de Gon said, what about theory? And that forced my student, that caused my student, Fred, to ignore my advice and take Pierre's advice and look at the theory behind the work. And this is what this will be about, mainly his work. And then the last one is kind of trying to be more philosophical. And I would like to look at the community of numerical analysts and the community of visual computing, which is computer graphics plus image processing. And I'd like to suggest that math does affect this, not too little and not too much. I'm going to show you special case studies for this, and I promise you it will be fun. Okay, that's the synopsis, which appears also online already, of these 4 lectures. So let's start with the first. Oh, one more thing. There will be papers that I will mention, but whenever it says A, that will be me. And if you want to see the paper, it is on my home page. And so if you, instead of writing here something long that nobody ever copies or looks at, I will just say Google my name and find my home page. And on that home page, you'll see the papers, and all of them are available. I shouldn't say that if I'm going to be on YouTube, but they are all available there from my home page. I didn't say it. OK. Any question before we start? Here's so now we are in the first talk already, and so I will show you, in fact, a presentation of a paper that we wrote in 2015. I was actually a minor contributor of that, but after showing you what we did, I'll go into what we didn't do. It turns out that this work opened quite a few avenues to consider in the solution of differential equations, as well as inverse problems. I will talk about that. And these are my collaborators, the only one not from China here originally. And then we have an ongoing, and I will discuss a little bit of this both today and on Thursday next week, my fourth lecture. So just motivation, what this is about. So it's not just computer graphics, it's also robotics. If you want to have a robot that actually can lift up something, it has to be soft touch. So when you have the contact, it is actually a deformable body. And also, for many computer graphics applications, you need to simulate, I don't know, sizzling steak, the motion of a pillow when you lay your head on it, and so on and so forth. All of those are, in fact, deformable bodies, and it's important to simulate them and also to calibrate them, as I will discuss in a minute. Lots of industrial applications. Lots of them are in facial expressions. There are people who have startups that just produce software for skin, simulating skin, facial, facial expressions, things like that. How do you simulate this? How can you use it for visual effects, and also for uses which require also quantitative results, not only qualitative. So if you want to do this with high quality, these simulations can be extremely costly, in fact. You're talking about hours and hours of computing. You have PDE, well, you can say that the underlying PDE depends on time and on space in 3 dimensions, although we are never going to look at the PDE like this, but it is kind of underlying it. So it's like the sound equation plus equal external forces plus maybe damping, some damping. And The thing is that we're not talking anymore about a domain that mathematicians would say, let it be a sphere or a square or something like that. Yeah, I mean, we're talking about articulated bodies, and I'm going to show you in a second one of them. And so the whole thing can be very expensive to simulate. Any function evaluation involved here can be very expensive, trust me. Moreover, so you have a model like that, and like we are all used to, I think, you have some PDE like this, maybe, and you want to find C. And likewise, you may have other, it's Young modulus, usually, that people are trying to find in the material that you're after. And also, there is damping, and you want to find the damping as well. This brings up difficult questions. So, what we do, fortunately, also in equations like this, you can discretize. By the way, I will emphasize numerical methods in this entire mini course. That is what it's about, scientific computing. So you have elastodynamics equations, okay? But people often don't look at they assume that this sort of differential equation, Laplacian in this case here, is already discretized. Okay, so in fact, what you do is you look at the variational level of these differential equations. They look much uglier than this, much more ugly. Here you're going to have some tensor, stress-strain tensor coming in, and so on. There are complicated things. And so what they do is they discretize using a finite element method. And then you have a moving tetrahedral mesh. I'm going to show you one of those. Okay, so there's a plant, and the plant is described by a fine surface mesh, a triangle mesh. Okay. But the simulations are done, of course, in 3 dimensions, not in two and a half, but in 3. And so there's a way of coarsening the fine surface mesh, just describing the surface, by a volumetric mesh consisting of tetrahedra. So the elements in the finite element method are tetrahedra, and that's a domain. It's not a sphere or a rectangle. It's much more complex, and it's important. The other thing which is important is, so your unknowns are going to be the values of the nodes. Each one of them is a 3-dimensional vector, yeah? A vector in 3-dimensional space, and it moves in time. So why is the plant moving? It's not walking. But there is wind, there's hurricanes. But even without hurricanes, there could be somebody is watering the garden, yeah? And so on, and so there's water, wind effects, and so on. And so this thing is moving, okay? And so you have a mesh in 3 dimensions, and these nodes are actually moving, describing the movement of the mesh. So the fortunate part here is that there is essential work on what is called Corotated finite elements from 2002, and then there is another work and software that takes a fine surface mesh and produces a coarser volumetric mesh. You know it's coarser because otherwise it becomes very expensive to simulate. Okay. And then you want to find the Young modulus and damping parameters. And so for this, we need data, and we do the usual thing. We find data and try to match the data, and in this way, find parameters of the differential equations. And here is the plant itself, in this case. And so you put the plant, you apply some sort of controlled deformation, and you measure with these Kinects. These are Kinect devices. Microsoft Kinect, and you make measurements. You get a sequence in time of point clouds of this plant, and you try to arrange to somehow make sense out of it, to track them, or it's called motion tracking. And now you try to use this motion tracking to you adjust the parameters so that the tracked motion agrees with what the differential equations would predict. It can be ugly, trust me. The fact that this mesh moves, where is it? This mesh moves means that when you move from one step to the, for those of you who are used to differential equations, discretize, you move from this step to the next step, you have a different picture. It moved, right? And so, for example, in ODEs, many of the methods for nonlinear problems assume that in one step you don't move too much, and so where I am is a good guess to where I will be. But that's no longer the case here. So you have difficult nonlinear equations coming up, all kinds of other trouble. So the saving grace is that sometimes you can use what is called physics-based simulation, which means if it looks good physically, then it's good, as opposed to satisfy a tolerance of 10 to the power minus 6. A big difference there. Okay, so the requirement is that it would look good and look good, but in a sense that you can actually use. Okay, and so it's the motion simulation, rather than the accuracy of the parameters, that is eventually observed. So sometimes you can have a difference, a significant difference, significant error in the Young modulus, and still the motion looks okay. It agrees. I'll show you an example of that. Okay, so that can be a saving grace here. And also you can use for the ODE solutions that you get a system of ODEs, very large because it discretizes in 3 space dimensions, so it could be 100,000 unknowns, moves in time. Yeah. And sometimes you can use methods, again I will show you which, that use large steps. I'll show you how that is done and what is good about it and what is not so good about it. That's going to come up in today's talk as well as the 4th one, the last talk that I will give here. Some of this has to do with geometric integration methods. Anybody knows what is geometric integration? Symplectic methods? I am a repeat visitor here, by the way, in IMPA. And one of the times, a few years ago, I gave a short course, Curso de Verão, on geometric integration. But that was already a few years ago, and everybody here is young, and so but it's methods that, like symplectic methods, methods that do, or methods that conserve energy, conservative methods, as opposed to damping, highly damping methods. Okay. Again, I will come back to this. So with this, let's move to deformation capture and modeling of soft objects. And so this is the paper. I'm going to have to change the talk here. This talk was not prepared by me. Anyone who knows me here would realize that immediately. It was prepared by Bain Wang. He's the main author. And this was a paper that appeared in SIGGRAPH. I don't know if if there's anyone here who does computer graphics, but people usually would love their papers to appear in SIGGRAPH. And often they submit to SIGGRAPH, and when they get rejected, they put it somewhere else. So that's my only paper in SIGGRAPH. But I was not a major author. And even you can see that it was, by the way, not me, because my name is misspelled here. And therefore, I'm going to go through it. I'm not going to stop into depth, because this is not what I'm, You will see why I'm showing it to you. Just both what's good in it and what's bad in it. That's basically what will be the lecture about today and some additional stuff. So people have used these finite element methods that I mentioned very quickly before, but even before that, people said, well, if I have this cloth, for example, it was cold yesterday here, but today I don't need it, but it's good for demonstration still. Then people use a system of masses and springs to model a thing like this. Okay, from 1908, and then there are models of thin shell that people used in computer graphics, and finite element methods, people from my own department, by the way, Batty and Robert Britson, who is now in Autodesk, but was in my department of computer science in University of British Columbia. And what they did was to tune the model and play with it and try to to see. I mean, they solved the inverse problem, but trial and error. Okay. The other thing that people did was to build special purpose systems where you can actually control everything better in order to come up with Young modulus values and things like that. But this is not general. And can be costly, and once you have the system and you move to your next application, you know, it's no longer pillows, it's now teddy bear, and you need to build a new system. And also sometimes it can do damage. The experiments can do damage to the plant. So we want to not assume that we have forces, but rather that we have positions as a result of experiment to which we are trying to fit our parameters. So there's a customized hardware system, an oversimplified reference shape. What is a reference shape? If you look once again, if you think of that plant that I showed before, what you see is the static shape before it starts moving because there's wind. Yeah. But that already includes gravity. Okay, and you want it without gravity because that will be what does not change if nothing happens. Okay, it's the reference rather than the static shape that does not change. And also, people usually ignore damping. And what exactly is the damping? They ignore that in computer graphics. Okay, and now there are reasons to do better. A major reason is because people have now advanced into trying to control an object like this and fabricate it. 3D fabrication, I think people have heard of this. If you want to fabricate it, you need to know the properties correctly and not just that they would look good. It's a different game that we are now looking at. It's a big change in computer graphics, by the way. So once a finite element method has been applied, you are left with something that looks like this. Masses times, so x are the positions of the x is the Q here. Sorry about that. X are the positions of these nodes of the mesh that I showed you before, and the accelerations. Okay, masses times accelerations plus damping matrix times velocities plus elastic forces is equal to external forces. There it is. I learned it by heart. I even know what it means. And so, yeah, I didn't do this. So there you have, once again, the nodes. The nodes are our unknowns x. Okay. In the Corotated linear model, what is that Corotated? So one thing I found by running around between computer graphics and numerical analysis and back, I found that lots of experts in finite elements have never heard of Corotated finite. I think that, have you heard of it? There you go. So basically, think of the Eiffel Tower, okay, made of finite elements, okay? And now think of the Eiffel Tower going like that, because it's not, it's just a toy. Yeah. So you can actually bend it, you know? It's flexible. Now, if you just use normal finite elements, then you're going to get a step function if you do a thing like this. And so you want them to be corrotated so that you won't have that effect. Something that does not appear in normal finite element applications. Okay? So this is called corrotation. And so before we get there, so the corrotation gives us a matrix R, which is the rotation matrix to ensure that the elements rotate together. This K here, before that, so the K Tx is the reference shape. And for the damping, everybody cheats by using this Rayleigh damping. You have the mass matrix and the stiffness matrix, and you have alpha m plus beta k, and you want to find alpha and beta, just two parameters. Thinking about it too much, because if you're going to put this thing in here and assume that m and k are constant and f is not there, then you can do an eigenmode analysis. Okay? Whereas if this is general, as it should be, you don't. And nobody knows what the damping should be. This is an open question, in fact, in engineering as well. So let's do that. Any question at any time, by the way? Just stop me if you have a question. This is a mistake here. It should have been this. Okay. So we have the unknowns are reference shape, Young modulus, Poisson ratio, and these two parameters for damping, alpha and beta. By the way, why damping? Why damping? So here is why. So this is, once again, my best chart. If you just look at the elastic forces, so this is pretty hard to stretch. And because it's pretty hard to stretch, you're going to have a stiff stiffness matrix is going to be stiff. It's going to have some high frequencies in there. But you don't see high frequencies. When I go like that, it doesn't go like this. Moves pleasantly, yeah, and that is because there's damping. Okay, damping saves the day. The question is, how much damping do we have? Because we want to fabricate this, so we would then need the precise value and not something that looks good. So the target here was that to do generic soft objects, not the special system, estimating from pure kinematic data, meaning on the solution values, and not force displacement measurements, and to estimate the reference shape, which usually people don't do, as well as this alpha and beta. As an overview of the system. So first, how do you acquire the data? It's another thing in inverse problems. People often have let D be the data. Here, these people actually found the data, got data. So, so you get, again, a system of point clouds by this Kinect equipment. And now you want to connect those point clouds into something that looks like a motion. This is called motion tracking, outside the scope of this talk, really. So there are the Kinect sensors, and there's the deformation here by twitching or you have, this is a homogeneous flexible body, by the way, otherwise known as something that you put your hot pot on. And you have a weight here and a tender hand by a female computer scientist from China. Cuts the cord, and the thing vibrates like this, yeah? And you measure how it moves. Okay. Opa. No. And here's an algorithm that I am going to try not to spend much time on for the motion tracking. The reason is that we didn't do anything about this algorithm. We just took available software from somewhere else. And to be perfectly frank, I don't even know the intimate details. But let me just throw words at you. So you have these point clouds, okay, C, and you want the triangle mesh that describes the plant. And you connect them by latent variables, okay? And so you're looking at the probability that given these point clouds, S S is the result. Okay, so it's a conditional probability, and that will be the maximum of this is going to be our S. Okay, so the latent variables, this is machine learning now. By the way, I'm going to try not to talk about machine learning in this mini course because oh, if you were here last week, then you may.
This week in my course in this program.
Hey, there you go. So then I am justified in not talking about it. But there is some special thing about here, nonetheless, that I doubt that all of it was covered. So this is, again, a usual. It's well known, in fact. So what you do is expectation minimization. It's a splitting sort of method. You iterate, and in each iteration, first of all, you calculate expectation, and then you maximize that. And so Z are the unknowns. They are the latent variables. We assume that the data C is normally distributed. Then the E step, you calculate an expectation. That gives you the first iteration on the latent variable Z, and this gives you a lower bound, it turns out, on the original, the actual probability distribution that you're trying to approximate. And so you got a lower bound, and then in the M step, you maximize the lower bound. By the way, this algorithm appears in the book of Bishop from 2007, so we're really not talking about new stuff. Although I doubt that everybody here knows it. Nonetheless, it is not new stuff. This book is, the problem with it is too big. Other than that, but it's there. The only thing here, which is, so you basically kind of improve your guess of the original problem in this way. In the M step, the important thing is, so the idea is to try to maximize the lower bound. And we want to explain the observation, but also to minimize a potential energy, a penalty of potential energy. And this is really the only place where Bishop from 2007 did not cover. So the way we do it, again, but this is not our work, the idea is you have forces, and for each force you can actually simulate. So you write a simulator, mx dot plus dx dot plus blah, 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 equal forces, okay? So you play with the forces. For each force, you know that you have already a system that simulates this thing, okay? And so here, there's a virtual force, so you invent some force such that it does the job for you, okay? So there's a paper by Schulman and so on, and not so on, but rather a bunch of other authors about that. I should say that, if I haven't said yet, that this amazing web address talks about, once again, about my papers, and one of the papers, sorry, I should say papers that I've co-authored, and one of those papers is the one I'm discussing here, and in that paper, this is described in detail and with the references. Okay, so if you are interested, there is a way of finding that starting from Googling me. This is not a very modest statement to make, but it's a way to get there. So it actually works. So this is for just the static shape of the first frame, just how well it actually does it. And look at this thing. I mean, you can hardly see the stem, and yet the result of tracking, you can see the stem very well. Data science works sometimes. On Thursday, I will tell you why it does not work, but today it works, okay? So there's reason to look at these algorithms. Yeah. So now, if we have this Young modulus and alpha and beta, then we've solved the problem because we have the correct motion tracking, okay? But of course we don't have them. And so what we do is we generate data in this way. And now we simulate the problem with the correct forces and try to match So and in this way to find the unknowns. Okay, so the unknowns now, so this is the inverse problem that I want to talk about. The motion tracking is also an inverse problem, but that's the one I don't want to talk about. This one, a little bit more, you have the reference shape and the material optimization, and so we look at this kind of objective function. So x hat here, not my notation really, are the result of the motion tracking for given Young modulus alpha, beta, and this reference. And now we simulate using simulation of the forward problem is the correct physical one, and that gives us x. And now we adjust these parameters so that x will be close to x hat. So reference shape is one kind of variables, and the other guys are another kind of variables. Okay. This is high dimensional because of x mainly, unless also it is highly heterogeneous, and then E also will have lots of unknowns. Okay. And the saving grace here is that the reference shape is relatively easy. If I know the rest of them, then the reference shape, all I have to do is adjust. I have a static shape, and I need to adjust it a little bit. That's all. That can be done independent of time. Okay. Whereas the material optimization, they are much harder, but they are fewer. That's the saving grace here. You know, where the most of the variables are, they are easy variables. The hard ones are fewer, and so it's natural. Moreover, they decouple very well because they describe completely different things. And so it turns out that if I freeze the reference shape and find the material optimization parameters, and then I freeze the material parameters and find the reference shape, and I iterate twice or so, it works. That's a week between for the success of this entire thing. And so here you have a static shape, and you want to somehow remove the effect of the gravity, yeah, and to obtain the reference shape, because then you need to use the reference shape for the remaining for the differential equation. We had the reference shape there in the differential equations. Okay. And so the idea here is to maintain static equilibrium. It's actually special, and again, we play with the force. We say, well, if it's static equilibrium, the force residual should be 0, and therefore we aspire for that, and something, and then use physics simulation based on this virtual force. Okay, and this thing actually ends up not being very difficult. The only thing difficult is to calculate the Jacobian of the force with respect to the reference shape. But after 2 or 3 pages of linear algebra, you get it. It's in the paper, if you must see them. And so here are 2 examples. This plant is more deformable, kind of softer than the right one, and so when it's softer, the difference between the reference shape and the static shape is larger than when it's kind of harder. Yeah. And now we are here into the hard part. For this, we match the full trajectory, not just at the beginning, and we use gradient-free downhill, like Nelder-Mead. I'm going to talk about that a bit later today. And so just to show you that it works, so this is the static shape and the reference shape. You see that they are different here, yeah? And the result of the material distribution that is obtained by this algorithm. Just to show you that all of these actually lead to somewhere, you can see that the tracking result and the simulation are not so far apart when the parameter was chosen correctly. This is a case where you don't have a homogeneous body, but a heterogeneous body, and these points describe the heterogeneity, the legs of these dinosaurs. This dinosaur is something that we would like to fabricate. Yeah? The legs are stiffer than the tummy, for instance, if it's going to be a toy. Yeah? And so these are control points, and so it's a piecewise linear in between those control points, but the control points basically means that the Young modulus is more complicated and it's not just one constant. If there's too many control points, we are dead. One reason is because we're using this primitive optimization method without gradients even. But in case you thought that the problem is easy, if you don't have homogeneity, then this is the map of the Young modulus, just two variables, and these colors signify ripples. So as you go along here, like that, you have ripples. So it's not convex. And you need to find what's in the blue here. The smallest is what's in the blue here. So you have a non-convex global optimization problem to solve. It can be easily very difficult. So there is a special procedure, again described in the paper, and independent of what I want to talk about here, for finding a good initial guess. Huge problem, by the way, not only for teddy bears, also for finding oils. Oil, for example, and all kinds of incredibly important problems. People were, only a few years ago, when Brazil was in a better shape economically, people were actually trying to build computer centers in Brazil in order to simulate problems that somehow relate to this. I'm going to skip this because it is independent of where we're going. So once we found the reference shape and the material optimization, this is based on data that actually assumed, so this is just one iteration, so we go back here and do the whole thing again. Track again, and then once again optimize this. And hopefully converge within a few iterations. I'm going to skip this. After so many approximations and assumptions, it's reasonable to see, it's a good idea to see that actually this thing works at all. And this is the wind direction and strength. Okay. Is it accurate to 10 to the minus 6? No. But it looks reasonable. Yeah? And sometimes it's good enough, especially if you make movies, for example. Nonetheless, you want to validate. And so, and again, how many people in the inverse community actually validate the results? Let's not talk about that. So here's the 0. Ground truth, and these are the tracking results and the simulation. Okay. So there's another one. But these are homogeneous bodies, okay? They're much easier than the general case. But still, that's not bad, isn't it? Yeah, it's, doing things like this is the domain of engineers when it comes to inverse problems. I mean, the mathematicians don't touch things like this. They assume that there is data, there is noise, always Gaussian, and you know exactly what percentage also. I mean, so none of this works here, yeah? I hope you realize this. Here you can actually see that we are missing something because this thing, there was high frequency here that was not observed here. Okay, so in fact, we were missing some high frequency. Here, very clearly, we're missing high frequencies. So that's worse than before in the sense that here you can see that there is something qualitative that we're missing. you can see, user interaction. Some wind effects. Okay. Can I stop this thing? Yeah, we had enough. Okay. Go ahead.
Will allow self-contact?
So,
Self-contact, like planes.
contact? Yes, there's contact, and it's going to be in the second contact as well. I only have 4 lectures. I will try to mention when it comes in. Yeah. Big problem, but to some extent, some people say it's under control. Different people will say different level of under control. So, okay, so let me tell you a secret. So the next stage was, the next paper of this team was to try to fabricate something. And as soon as we tried to do that, a huge number of problems arose, and I'm going to mention a few of them. Okay, so this is the beginning, not the end, the paper I just showed you. So the discretization of the ODEs in the presence of high frequencies, it's a non-trivial problem. I'll mention it today as well as next week. Highly non-convex, highly nonlinear optimization, I actually tried to point it out. So today I'm going to the last part of today's lecture, I'm going to do a survey of optimization methods. Somewhat dubious statistics, the topic of next Thursday's lecture. Okay, homogeneous material brings the idea of homogenization methods. There are some papers about that in the literature. I will not mention that at all. I will talk only about the colored one. So, but nonetheless, let me mention the others. A more realistic damping model, everybody wants that. It's not everybody, you know. A bunch of people want that. Nobody has good answers. And better measurements. I mean, the measurement devices that we had could not capture Poisson ratio at all. You could vary it and you don't see it. What I'm going to talk today about more is these 2 questions. How do you discretize an ODE system in the presence of high frequency? And then optimization. At some point, we should also, what should we do? Is it better to just talk until we're done, or that we take a break sometime for 5 minutes? All right. That's right. Yeah, when I see more than 3 or 4 pairs of eyes closed, I'll know to stop. Okay, so first of all, let me talk a little bit about soft material models, which is what's behind all that, and then large step methods that people used in practice and what's wrong with them. So there's a fat book by Cierlet from 1993 about deformation in 3 dimensions. And again, it is convenient to semi-discretize without ever forming a PDE, the easiest case of which would be something like this. So we're going to talk about ODEs, but that means that 3 space variables have been discretized already. What did I do? OK, I freeze. Tá bom? So we discretize it either with this FEM, Corotated maybe, or a mass spring system. The difference, by the way, is that if you do the finite element method, that you're going to get a matrix with a whole spectrum of frequencies, whereas the mass spring system, you're going to get high frequencies and low frequencies, but not necessarily the one in the middle. That makes it easier sometimes, depending on the method that you will use. Can make it easier to simulate. And so you get an ODE system. I've switched from X to Q because I like Q and X was what being wanted. So masses times accelerations, Q, is equal to the totality of the forces, which are the elastic forces, which depend only on Q, plus damping forces depend on Q and on the velocity, V. The velocity V is the derivative of Q. So these are going to be the velocities of the nodes. Remember, we have nodes of this tetrahedral mesh, and they move, yeah? And so the speed of the movement. And then external forces like gravity and like collision, for example. They come in here. Gravity is simple, collision is not simple. But there are methods to handle collision, and some packages to handle it as well, and they use some reflection so that they don't even have to change the step size. It's important in some of these applications to keep the same step size because it relates to the rate of measurements. So there it is. And so is everybody with me on this? This is important to somehow remember. The system of equations. Again, the boldface means vector, so it's a vector of unknowns, can be 10,000 of them. I think that in the paper I just showed you, we had the largest 15,000, but it comes from discretization of a three-dimensional body. It can be 100,000 easily. Big vector functions. Yeah. And the elastic forces are the gradient of an elastic potential function. Potential energy. And the damping, we are going to write it as a D times V, and D will depend on Q and V. And in the simplest case, W will be quadratic, and here we are therefore going to be linear, so it's going to be a linear something constant times the vector Q. And then when I take another derivative, that constant matrix called K will be constant. Quartic problems arise as well. It's called I forget what this STVK is for. You can have nonlinearity, but a special form, this R matrix that I showed you before, that can be nonlinear, depends on Q. And there's something called neo-Hookean, where you can actually have energies that are not even positive. You can have actually negative definite elements. So we write it as the first order system, okay? So the first one says that the derivatives of Q are V, and this one says that the derivatives of V, which are accelerations, are equal to the mass inverse times the F total. And now we write this as a matrix. It's kind of linearization, exact linearization. We emphasize the important part, and then the rest we call G, okay? So that's going to be minus M inverse K here and M inverse D here. Okay? And K is the tangent stiffness matrix at Q. Okay. That's the system that we look at. And again, the stiffness matrix does not need to be positive definite in some situations. Depends on the model that you're looking at. So there's some significant modeling problems here as well. And moreover, it's important once again to realize that when I do this, you're not going to see high frequencies. They're damped. So they're there in K, in the stiffness matrix, but they're not there. They are there, but you don't see them because they're damped. Unlike, for example, sound, where they're not necessarily damped. You actually do have to look at high frequencies. And so now you want to use a step size tau, which is not like the high frequency, not like high frequency, but large, commensurate with a smooth movement of my shirt. Big difference. We were talking about the step sizes that may be 10,000 times larger than what you will have to do by Nyquist theory if you were going to simulate a high-frequency oscillation. This is stiffness, but of a high-frequency type, not of oscillatory, highly oscillatory type. Yeah. So you can't use explicit Runge-Kutta for this. And if you use implicit Runge-Kutta, then I mentioned this before, when you move from the current step to the next time level, you have a problem because you don't have a good initial guess, unlike normal ODEs. If you ever took ODE courses, numerical solution of ODEs, you always assume there that the problem of solving nonlinear equations per step is not difficult because you have a good guess of what the solution at the next step is. Here, it's not so simple. So the way that Baraf and Witkin solve this, and they say, we're going to use backward Euler because we don't want to see high frequencies. So we use backward Euler, which is a method that anybody knows what is backward Euler? Anybody does not know what is backward Euler? Let me write it down. Let me write it down for the average. So let's say that I have, I think it was called like this, something like that. This is a diff and f, yeah? And u is my q's and v's together. Yeah? And I'm now at the time step tn, and then I take a step size tau, and that will be my next time level, n plus 1. Okay, so there is time from tn to tn plus 1, like that. And so backward Euler says u at your next time level is given by u at the current time level plus tau times f times u at the next time level. That's backward Euler. If you do forward Euler, which means un here, it blows up because tau is large. Okay, so you have to do something implicit, meaning you have here an implicit guy. So our known guy is this, our unknown guy is this, and it appears here and here, and therefore you have a nonlinear system to solve at this step. And so they said, oh, this is difficult to solve. Okay, and therefore, let's do applied Newton's method for nonlinear equations, Newton's method, and take only one step of Newton, not one iteration of Newton's method, and then not look backward. Like just do it one iteration. And so that actually was called a it's one of those things that people in graphics discovered 20 or 30 years later after the first time people looked at it. And so, in fact, this is called semi-implicit methods, known since the 1960s, but not in this beautiful connection. See, that's the important part. So this semi-implicit method, and so again, you just apply Newton's method for this, and just one step, one iteration. You don't check convergence. You just do one iteration and continue for the next step.
Why can't you use the explicit Runge-Kutta?
Sorry?
Why can't you use the Runge-Kutta explicit?
The backward Euler.
Why can't you use the second option? Why?
Oh, explicit.
Yeah.
The explicit, if you look at it, for explicit method, you need the step size times the highest frequency that appears in the stiffness matrix should be bounded by 1 or 2, depending on whatever, depending on the method. And that means that your step size must relate to those high frequencies that you don't see. Okay? Now, what you want is the step size that covers a few of those unseen frequencies, and therefore you cannot use explicit methods. This is a book of mine, by the way, where I use their method as an example. It's not my invention. I just repeated what they did. There's something called generalized alpha, which is also popular in Disney animation. They use generalized alpha. The problem with these methods is that it introduces heavy damping. Okay, I mean, the reason why you don't see the frequencies, high frequency, high oscillations, is that heavy damping is introduced, and now this depends on the step size, not on this material. It depends on the step size that you use. And so this, if you're going to use it for fabrication, I mean, the step size gets into your simulation for the fabrication. Okay, you're really solving another problem. You're not going to get results that are quantitatively correct. So in an example, easier to see here. So we take a bar, kind of a soft bar, and twist. Okay? And if you use a method that is more careful, you get this sort of twist. This is already rendered. Okay? So with a tetrahedral mesh, it looks like that. Okay? Twisted. So this guy is the same as this guy, but here it is just rendered so that you can see it better with shading and lighting. Okay? This one here is Beckett-Euler. Okay? So again, this is implicit midpoint, and this is Beckett-Euler. Same step size. And so you see that, here it's easier to see, that, that here, I mean, this is obviously in error. Let's say that this is exact. This is obviously in error. Okay, clearly, I mean, we can see that it is in error, but it is not a random error. It is actually the same sort of twisting, but not so much. Okay? Like waking up in the morning. You wake up in the morning, you brush your teeth, you know, you go slowly. You know, after lunch, you brush your teeth much more energetically. Yeah? Same thing here. Yeah? So Beckett-Euler is not just any error. It actually is similar to the same sort of simulation, but more slowly. Just loss of energy. And if you do semi-implicit, here it doesn't look so great, but also it's the same sort of thing. Also the semi-implicit. And that's why it worked. I mean, when you have a paper from 1998 that is mostly used by a whole community, something must work there. Otherwise, it does not happen. It's not a theorem. People use it all the time. So yeah. This method here is really the one which is most used in practice today. We are trying to change that. So this is a mysterious method that I will come back to on Thursday next week, an exponential method. Okay. And so we do a simple analysis to see what's going on. What we want to find out is why does the Beckett-Euler look real except with less energy, you know, instead of just an error. So we look at one equation, just one equation, not 10,000, one equation, with the damping factor D constant, and the matrix big K is now a frequency squared, one frequency squared. And we assume that this this omega is large enough. And so we can do an ansatz. We can assume that the function Q is exponent of lambda t, and lambda now is an unknown. Okay, and so you substitute this here, and so the derivative of Q will be lambda times Q, times the same exponent. The second derivative of Q will be lambda square, yeah? Times the same thing. You drop the Q and come up with the equation, lambda square plus d lambda plus omega square equals 0. And we can solve that. I can solve that even. And here's the solution, yeah? Notice that we assume that omega is large, so this is a negative, therefore this is an imaginary part. And this is the real part. And so the exponent, if we look at the magnitude, we want to see how the damping works, yeah? This is what matters. And so we want to see the magnitude of the exponent of lambda times Tn. Tn is the step here, yeah? And so that will be the exponent of the real part of lambda times T sub n. And therefore, it's only the d that counts. This guy does not count. Okay, minus d over 2 times t. That's the decay of this or the, for this or the. And now we say, what about Beckett-Euler? let's set D to be 0. Opa, what did I do? Yeah. Let's not set D to be 0 yet. Let's write backward Euler, which is the same as semi-implicit because this one Newton iteration is when it's linear, it's the same. So, and so we have that the solution at time n is equal to this matrix times the solution at time n minus 1. I wrote here from Tn to Tn plus 1, but the same thing is from Tn minus 1 to Tn. So there's a matrix T which is independent of the step size. Okay, this does not depend on n. So Qn Vn is equal to T times Qn minus 1 Vn minus 1 equal to 2T squared Qn minus 2 Vn minus 2 T cubed and so on. Okay, and so what people do in numerical analysis is to say, I have to look at T to the power n. And for this, I have to look at the spectral radius. What is the maximum eigenvalue of T to the power n? And here it is. Okay, so the eigenvalues are 1 over 1 plus minus I times I is the square root of minus 1, tau omega, and this is the spectral radius. Okay. And so we can say, let's now take D equals 0 here. Okay, so we are assuming that the given problem is actually the oscillations don't die at all. But now something will die because we're using backward Euler. Okay, so in fact, we will say that we are looking at a D backward Euler. What the method introduces by comparing the actual reduction here that you get because of T to the power n, the rho is the spectral radius of T. This guy, we equate it to a ghost D, yeah? The D that we will have to put in here in order to get the same sort of reduction in a similar differential equation. Yeah. So it's a ghost differential equation like that, okay, with the original D, which now is 0, replace that by D of backward Euler. And this dBE, when you basically take log here, and the n disappears, and the 2 disappears, and so you get the dBE times tau is equal to the log of 1 plus tau omega squared here, divide by tau. Okay, so that is your artificial damping factor. So it actually does relate to the same. The point is, it does relate to the same sort of differential equation. Okay, but with an artificial damping that comes from the numerical method. So it's better to write dBE over omega and obtain this expression. Why is it better? Just checking if you're awake. It's better because this guy depends only on tau times omega. Tau is the step size. Omega is the frequency. And this expression depends only on the product of the step size and the frequency. Okay? And so I can actually plot it. So dBE over omega depends only on tau times omega. Okay? And there it is. This is the damping for backward Euler. It is worst in some sense, in the sense of divided by omega, when tau times omega is around 2 or so, order 1. Okay? But then when the frequency is high, let's say you fix tau and take higher and higher frequencies, which is what we did for this, then the change is not so bad, and that's actually very, very nice, because it doesn't depend on each frequency, high frequency alone, and they're kind of similar to one another. And so you can have, here's an example, okay? So this is the ghost ODE for backward Euler, and this is the actual result of backward Euler. So the point is that you only want to look at the damping here, yeah? How it decays. Likewise, whereas the actual solution doesn't decay at all, right? The exact solution of this differential equation does not decay at all. And here we take high frequency compared to tau equal 1. The step size equal 1. And so the exact solution does this. And the ghost differential equation solution is this guy here, the pretty one. And the step size of backward Euler gets you directly to where the damped one is. So it quantifies the damping and in a sense suggests that maybe, in fact, it makes sense to expect that the result of the backward Euler and semi-implicit to also look like the same twist as we saw, but more slowly. I have also a video that I will show you on Thursday next week that shows this better. So here is a collision. There it is, collision, Alex, with a ball. Actually, this is the picture. A ball comes, the children are playing ball in the backyard, and then there is laundry hanging, and there's the ball hitting the laundry, okay? And so the energy curve for the implicit metpooling is like that, whereas for backward Euler and semi-implicit is like this, much lower. So there's a loss of energy, but again, a similar sort of action, okay? So this is implicit midpoint, and this is backward Euler, less energetic, semi-implicit, less energetic and not quite correct. Here, we get actually something called, because if you have exactly the same motion but slower, and we're talking about creating a movie, then what do I care that this is slower? I make it faster in the movie. And in this primitive way, everything is solved. But this is not as simple as this. Again, it is not quantitative. And also, if I have here a sheet that different material, okay, then because it's different material, the correct motion goes like that, but backward Euler does not see it because the diffusion, the damping is because of the method, not because of the material. So it's the same material. It doesn't matter if the material change, the damping is the same. So you get qualitatively a different picture. Where am I? Ooh, wow. I'm going to skip this thing and go to optimization, because it is optimization that is going to be with us. Yeah. So once again, if we go back to the videos that we show, we have a reference system X, and we apply, as I mentioned, a splitting scheme, alternating solving for X and for the Young modulus and the damping parameters. And let's assume that the X is done. The question is, how do you deal with this U? Okay, how do you deal with those other parameters? So this is directly the inverse problem that we are used to some extent, but for underlying hyperbolic PDEs, not parabolic or elliptic, but hyperbolic PDEs. It's important to understand that there is a big difference there. The essential difficulty in solving inverse problems in practice is completely different when you have a hyperbolic PDE, such as in oil exploration, the full waveform inversion, for example, and when you have EIT or any of those, some of the other examples that quite a few people here have been looking at. I want to do a crash course, 15 minutes, of optimization. Is that okay? Are we still awake? Well, actually, some of you can sleep for 5 minutes now. But somewhere along the line, we are going to wake up. So again, change of notation. But we are switching worlds, and somehow in optimization, everybody uses this notation. And so let me use it too. So now f is not forces, it's an objective function. And x is what used to be q, now it's x again, just variables, x, okay? And nobody dares to change this notation, okay? So yeah, optimization variables and objective function. And we are going to denote by star the optimal solution or an optimal solution. And for simple examples, this function in one dimension has these minima, local minima, many local minima here, one global minimum where the function is the lowest. Please stop me if I go too fast on this because it's this kind of basic stuff and I do not know, I know that some of you know it all too well. I realize that. Okay, now in some other situations, x is restricted to be here, and so the minimum will be here, not here, but here. You can also have discrete problems. So there's lots of optimization problems, and we are going to look at continuous and forget about discrete. We are looking at unconstrained, even though constrained every once in a while shows up. We're going to look at local optimization, even though global optimization occasionally shows up. And stochastic versus deterministic, again, sometimes it shows up. All the algorithms we look at are iterative. So we start with an initial guess, x sub 0. And sometimes the result depends on what x sub 0 is. And we iterate iteration called x sub k until we hopefully converge to the optimal solution. Can be difficult to solve. I mean, lots of people nowadays are looking at optimization. It is an area that is being rediscovered nowadays. And it is often not so clear which method works best, and it depends on not only on the optimization problem, elliptic, hyperbolic, but also on what we want. What is it that we want out of the solution? That is a huge, important question in machine learning. Often they want completely different, the goal is completely different than when we talk about parameter identification. Right? And that changes the decision of what algorithms work better. And the idea is often to recognize something simple, such as this quintessential data fitting problem in least squares, and to find structure and to be able to use the structure. Convexity is very important if the function is convex, if for any alpha beta, such that alpha plus beta is 1 and they're non-negative, f in the middle is below the line. I mean, actually, it's better to show it in a picture. This is a convex function because if I take a point here and a point here and pass a straight line, the actual function is below any straight line like this. Okay, so it's the below. Yeah? So that's a convex function. Convexity means that you don't have to look at, once you find the minimum, that will be the global minimum. Life is so much simpler with convex functions. In one dimension, we know from high school, I think, that where the derivative is 0 is a critical point, and that can be a minimum or a maximum in one dimension. And to find out if it is a minimum or a maximum, we look at the second derivative, and it is a minimum if it is 0. It is positive where the first derivative is 0. In more than one dimension, life is much harder. So for example, for this function that we saw before, this guy here, this one here, we just calculate the gradient in one dimension and solve this nonlinear equation, obtain this solution, check the second derivative, it's positive everywhere, and therefore this is the minimizer. Life is much more difficult in 10,000 variables. And so here, for example, the function f derivative becomes a vector, a gradient vector, gradient of f, which is the vector of first derivatives. And the h of x, the second derivative, becomes a matrix, a Hessian matrix of second derivatives. And Taylor expansion says that if I am at x and I'm moving in direction p, then f of x plus p is fx plus the inner product of the gradient with p plus this quadratic form plus higher order terms in the norm of p. And so if I take p small enough, in the norm small enough, then like I'm going to look at direction p, evaluating where I'm going to go from this point. then it is clear that I must have this gradient 0, or else p could be in the wrong direction, and this guy is p squared. So this one must be, if the gradient is not 0, then this dominates that, and it can be of any sign. Therefore, I cannot go, I can always go further down. So for an optimum, the gradient must be 0. So the gradient must be 0 here, and that would be a critical point. In more than one dimension, I can have a minimum point, right, like here, minimum point. I can also have a saddle point, like over here, where in 2 directions it goes up, and in other directions it goes down. Anybody hasn't seen this before? And so we're looking for a critical point as before. The gradient of of f is 0. That would be a critical point. Okay, this is a gradient. And if the Hessian matrix is a positive semi-definite, then that is a necessary condition for a minimum. If it is positive definite, i.e. it's also non-singular, then it is a sufficient condition for an optimum, for a minimum. Not a global minimum, a local minimum. And gradient descent methods, you have to look at what is the descent direction. So let's say that I'm in IMPA, and the time is kind of late, and I want to go home, and I have to find a way where it goes downhill until I get to the Lagoa. And so I want a direction that will take me downhill. Yeah? And so that would be a direction such that the inner product of this direction P and the gradient is negative. Okay? And if I have such a direction, then there will be an alpha small enough such that f at x plus alpha p is less than f of x. So if I start going down, then I will be lower than where I am now. Okay. So that's a basis for constructive iterative methods. And where am I? So we have an initial guess, generate iterates. Each time f would be less than fx plus fxk. That means I'm looking for a local minimum, okay? Because I'm going downhill, I have no way of getting and finding that there is a smaller minimum. And there are many methods that look like this. At a given x sub k, we calculate the direction p sub k, a step size alpha sub k, and form a new iterate xk plus 1, where the direction pk would be minus positive definite matrix bk inverse times g. So g transpose times pk would be minus g transpose bk inverse g, and therefore that would be negative. The simplest such method is with this bk equal identity. That's gradient descent, just descent in the gradient direction. The hardest one will be Newton, where you choose the Hessian matrix, assuming that it is positive definite, to be bk. And then we set alpha sub k equal 1. And then if we are close enough to begin with, then it will converge quadratically very fast. The most popular method for packages is BFGS. BFGS is a method that basically says, let's approximate it in some sense, but retain positive definiteness and do everything much simpler, because really all we need is bk inverse g rather than bk itself. Not bk, but bk inverse g. And so we can take advantage of that. And Gauss-Newton I will talk about in a second. And then this is the most popular method in machine learning, and therefore maybe more generally is stochastic gradient descent. In machine learning, they have huge problems, not just large, huge. And if you have 4 billion unknowns, then you don't want to see any matrix, any matrix. And identity is yeah. Okay. So Gauss-Newton, I will talk about it again. The quintessential problem nowadays is data fitting. You're looking, here is a nonlinear data fitting. You calculate the Jacobian of the function phi that arrives here, and so this is the gradient, okay? And then Gauss-Newton says, instead of Newton's, the full Hessian, just look at A transpose A here. And then this corresponds to solving a sequence of linear least squares problems. Okay. We'll talk about it again. And then we perform a line search using what is called Armijo time stepping. Cut the step size by 2 until you get decrease. And I'm jumping here a lot. If you have a large condition number, then gradient descent does not work very well. People use Gauss-Newton or other things. But again, it is not possible to do that in many very large applications. Fortunately, many very large applications do not have large condition numbers. And that is where machine learning community and numerical analysts diverge at this point. To calculate the gradient, I'm going to skip this and to skip this as well. I want to talk about non-convex problems. Because again, this is something that if it doesn't hit you, you don't realize how terrible it is. So let's say that you have this sort of function even in 1 dimension, okay, with lots of minima and things like that. Gradient descent, what does it mean? We always go down. That means that if we are here, we will find this minimum. And if we are here, we find this minimum. And if we are here, we find this minimum. But it's always going to be a local. You don't know if you are even in a global, you found a global one. It's a much harder problem. Okay. And so one approach is this one. Sometimes it's hard to beat this one. You have computers, assign each one the same code with a different initial guess, solve, compare, and be happy, or not. And that is what we had here in this example from computer graphics. You see? And likewise, again, in searching for oil and many other applications. So just to show you how difficult it is, remember we had in the least squares objective function there in the PowerPoint presentation. So we take this signal, we shift it a little bit, add a little bit of noise, and here is the least squares objective function. It's terrible. It is really not just one local minima, not just 2 or 3 local minima, a lot of local minima. Okay. So just like that, you get difficult problems to handle. And so there is a method called inverse harmonics that reminds me of what Samuli, in fact, has been doing for EIT, but in a simpler way. But I'm not going to steal anybody's talk from next week. And that's a possibility, but in general, there are difficult problems there. Some people looked at optimal mass transport in order to improve the objective value to be more convex. Okay, beautiful talks and beautiful papers, but I don't know that they've succeeded in actually making it work for the full waveform inversion, for example. And people talk a lot about convexification. Try to do some sort of convexification of the given problem because it's somehow special and you take advantage of the specialty of the problem. Often it amounts to a splitting method, really. Okay. This is just conclusions in order to finish, but I think that we can finish anyway because the hour is late. And so just to mention that on Thursday, I will talk about data manipulation and data completion. And there was a little problem that I mentioned before of data manipulation in that computer graphics talk that I showed you before. I'm done. Nada.